We're going to talk very briefly about this Frenet Serret frame, or to avoid mangling the French language, we'll call it the TNB frame. Not going to do a whole lot with this. There's a lot you could do with this. We could spend a long time on this, but that's really something that's more appropriate for like an elementary differential geometry class. What I want to do is just give you introduction to the main idea of it. We will do a couple calculations on some simple examples, but there's a lot of formulas and relationships that we could get into that we're not going to touch at all. So there's three main vectors associated with the TNB frame, and the idea of it is that it's a moving coordinate system or a moving frame of reference associated to a curve. So for instance, if you imagine like the motion of a satellite, or just the motion of an object in space, the idea is that there's a certain coordinate system that you can use to analyze the motion of this object, and this coordinate system is going to change along with the object as it moves. And so at any point along the curve, you're going to have these three vectors that are giving you what's called an orthonormal basis in the language of linear algebra. So what that means is there's three vectors that are all mutually perpendicular, so they're all at 90-degree angles, and they're all unit length. They're all length 1. It's very analogous to, say, the IJK. So the IJK coordinate system, just in ordinary 3 space, is what we call an orthonormal basis. I, J, and K all have length 1, and they're all mutually perpendicular to each other. So it's the same idea here, except in this case, instead of being a static frame where they just are the same 3 vectors throughout all time, this frame is changing along the curve as you move. Okay, so what are these 3 vectors? So let's talk about them. So the first vector is the unit tangent vector. This is something we've already studied, right? We talked about the vector derivative, or the velocity vector. The unit tangent vector is just the normalization of that vector. So you just take the velocity vector, normalize it, so you just want to keep track of the direction. Okay, so we've already talked about that. Now the unit normal vector, the way the unit normal vector is going to be defined is it's going to be the normalized derivative of the unit tangent vector. Now, it's very important to understand that that's not saying that it's the normalized second derivative. So it's not the acceleration vector. The acceleration vector is something different. Acceleration vector says take the second derivative and then you could normalize that. What we're doing is we're saying just keep track of the direction given by t and then take the derivative of that. So how much is just the direction changing? Not the direction and the speed, but just the direction. Take that derivative and then normalize it, because that derivative may not be a unit vector, but we're going to normalize it to make it a unit vector, and that's what the unit normal is. And what this vector indicates is the change of direction. So it tells you how the unit tangent is changing, and it captures kind of how much the curve is failing to be a straight line. It's capturing the deviance from being a straight line. But in more than just the curvature also captured the deviance from being a straight line, but it was strictly a numerical quantity. The unit normal actually tells you kind of what direction it's changing direction, if that makes sense. And when we look at when you visualize this, when we look at some pictures of it, I think that'll make sense. Then the third one is the unit binormal vector, and the definition of this simply says you take the cross product of the tangent, the unit tangent, and the unit normal. But what this ends up meaning is that it's a normal to the plane containing the unit tangent and the unit normal, and that plane is called the osculating plane. The best way to think of the osculating plane is it's the best plane that the curve lives in. So if you had a plane curve, the osculating plane is just the xy plane. It's just the plane that the curve lives in. So the osculating plane is saying what's the plane that the curve best lives in, close to that point. And then the unit binormal is just a unit normal to that plane, which you get by the cross product. Now, since the t and the n, the unit tangent and the unit normal, since those are already unit vectors, when you cross t cross n, you automatically get a unit vector. So you get a vector that's perpendicular to both of those, and it's automatically a unit vector by what we know about the cross product. So automatically now we get 3 mutually perpendicular vectors. Oh, I didn't mention, why is the unit normal perpendicular to the unit tangent? Well, it's because we know that we showed previously in one of the videos, a couple videos ago, that if a curve lies on a sphere, so if its length is constant, so if in 2 dimensions it lies on the unit circle, or if in 3 dimensions it lies on the unit sphere, we were able to show that the derivative was always orthogonal, right? So if a curve is lying on the unit sphere, well, actually not just the unit sphere, but any sphere, then its derivative at that point has to be at a 90-degree angle. And so since the unit tangent always has length 1, it has to lie on the unit sphere, which means its derivative always has to be orthogonal. So from that, we get that the unit normal has to be orthogonal to t, and by definition of the cross product, the binormal is orthogonal to t and n. So these are all mutually perpendicular, and they're all unit length 1. So that's what we call an orthonormal basis, similar to ijk. So this TNB frame came about, like the mid-19th century. It's really the beginning of this big subject called differential geometry, which is an enormous subject that has grown since then. It's been generalized and abstracted and made very modern all the way until the current day. It's a very active research area today. So it's kind of an example of a branch of math that's, even though it's 150 years old, it's just kept growing and growing to the point where people are still working on it today. So let me draw kind of the best picture that I can for these 3 vectors. So let's say that we have a curve like this. So let's say we wanted to kind of sketch what would the TNB frame possibly look like at this point right here. So we already kind of know what the unit tangent vector should look like. So let's draw something about what the unit tangent vector might look like. So there's a reasonable looking unit tangent. Now here's what the unit normal might look like then compared to that. So that might be a unit normal. Notice how the unit normal is pointing in the kind of the convex direction, indicating that the tangent is turning to the right. If you imagine, if you're say you were driving along a car in this curve, so the road would go to the right, so you would have to be turning your steering wheel to the right, if you wanted to stay on the road. So that's why the normal is pointing to the right. Now this would be a perfectly good TNB for a 2-dimensional plane curve. You'd have to use the right-hand rule, and you would see that since since t is, then we're going clockwise to get to n, then we would get the binormal would be pointing away from us, right? So if you remember about the right-hand rule. Now, if this is a space curve, it's a little hard to know, exactly where the binormal would be, because we have to kind of see, you have to move your perspective to see kind of what this would look like in 3 dimensions, but maybe it would look something like this. And you see, I've kind of tried to draw their kind of the 3 right angles to indicate they're mutually perpendicular. Maybe it's not the easiest to see that, but notice all these have the same length. And so this would be moving along now as you go along a curve. This would be moving with it. So let me give you the formulas for it, just the basic definitions of these before we go any further. So we've already gone over. So let's suppose this is r of t. So we already went over that the tangent is defined to be r prime divided by the norm of r prime. I'm going to leave off the t's because we don't need it. The normal then is t prime normalized. And then the binormal is t crossed with n. Okay, so we can take these as definitions. Now, having said that, if you really wanted to study these kind of TNB frames and actually calculate them for specific curves, there's a bunch of alternate formulas or alternate computations you want to go through. Kind of like for the curvature, remember the curvature, we defined it as, this norm of dTds. But then we said there's all these other alternate formulas. So we got 2 alternate formulas, one involving just the derivatives of r, other ones if it was a plane curve or graph of a function. It's kind of the similar thing for this. There's all alternate formulas for these just in terms of the derivatives. So you can express all of these just in terms of the derivatives of r. And then that makes it much easier. It's still difficult, so it's still really messy, but it's at least possible, say with pencil and paper. But doing it using the definitions here, it really kind of gets out of hand. So what we're going to do is just do the kind of standard example of the helix, which is the kind of prototypical example of a space curve. And then we'll do for something called the twisted cubic. So let's go ahead and look at that helix, and let's calculate the entire TNB frame. Okay, so the first thing we need to do here is we're going to calculate the unit tangent. So we'll do that by first calculating the derivative, which in this case is minus sine cosine 1. Then we need to take the length of this. So square root. So since it's minus sine, that's the same as if we squared sine. So sine squared plus cosine squared plus 1. So we get just square root 2. So that's one of the reasons why the helix is one of the few that you can actually do pretty straightforward by hand, because it ends up having constant speed. So this means our unit tangent is 1 over root 2 minus sine cosine 1, because it's r prime divided by its length. Okay, so now let's look at the normal. So this one's a little bit trickier to get, because we have to differentiate this t prime. So let's find the derivative of this. Again, notice this is slightly different than r double prime, because r double prime would say, let's take the second derivative. That would be the acceleration. This is not the acceleration. This is the derivative of the unit tangent. So we get 1 over root 2. I'm going to differentiate minus sine is minus cosine, minus sine, and 0. And then I need to divide by the length of this, which you may kind of already see, because if you notice, it's just going to be cosine squared plus sine squared. So without the 1 over root 2, this has length 1. So it's 1 over root 2, square root cosine squared plus sine squared. So that gives us 1 over root 2, because cosine squared plus sine squared is equal to 1. And that means that our normal vector, our unit normal vector, is the 1 over root 2 minus cosine minus sine 0, all divided by 1 over root 2. So those 1 over root 2's go away. So we just end up getting minus cosine minus sine 0. Now we move on to the binormal. And the binormal, we just take a cross product. So we're going to take the cross product of t with n. Now, because with the cross product, one of the properties is I can take out constants. So instead of having the 1 over root 2 times minus sine t, let's just put the 1 over root 2 outside of the determinant. And then we'll also take a minus from the n. So in other words, it's going to be this 1 over root 2, and then the minus from here is all going to come out as a minus 1 over root 2. So it's minus 1 over root 2 times the cross product of minus sine, cosine, 1, with cosine, sine, 0. So we get minus 1 over root 2. So now when we do the cross product, it's going to be cosine, sorry, it's going to be 0 minus sine, so it's going to be minus sine. For the j component, we're going to get minus a 0 minus cosine, which is going to be positive cosine. And then for k, we get minus sine squared minus cosine squared, which is negative 1. And if we now go back and distribute the minus across, we see that it's 1 over root 2 sine minus cosine 1. Okay, it's just distributing the minus back through it. Now, what we've got now is all three of them. So let's summarize all three. Let's just write all three of these here at the bottom. So we got our unit tangent was 1 over root 2 minus sine cosine 1. Our unit normal was minus cosine minus sine 0. And then our unit binormal is 1 over root 2 sine minus cosine 1. So a couple things to notice here. We already noticed that the speed was constant, so this has constant speed square root 2. We actually saw that earlier, before this video. Notice that the normal minus cosine minus sine. So if you think of, if you're going around, remember that the position vector is cosine sine t. So what this is saying is that at any point in time, the normal is pointing in the opposite direction of the projection of the position vector onto the xy plane. Okay, so let me say that again. What it's saying is if you ignore the up-down part, if you're only looking at the part in the xy direction, in other words, if you just think of it as a circle, going around a circle without going up and down, then the unit normal is pointing directly towards the origin. And what that means for the helix is that the normal is always directly pointing towards the z-axis. So it's always going to be pointing directly pointing towards the z-axis. In fact, its tip will always, in this particular case, this tip will always hit the z-axis. And then the binormal, which is the cross product of these two, its first and second component are the opposite of the tangent, but its z component is the same. So it's always pointing kind of in the up direction, but in the first two components, it's just the opposite. So it's kind of like the tangent, except it's always pointing up. So let me go ahead and show you what this looks like visually. So we'll go to the CalcPlot 3D and see what this looks like, and you can see the entire frame as it moves around the helix. Okay, so here it is. Let's take a look. Now, I'm not going to put the frame in just yet. What we'll see here is just the position vector as it moves along the curve. I think we've seen this before, so there it goes. Let me speed it up just a little bit. So, kind of a little bit slow. There we go. And I'll move it around just so you can get some perspective. There you see it going through 1, 0, 0. And it goes up and away. Oh, Okay, now let's look at it with the frame. So what I'm going to do is go on here and I'll take off the trace vector and I'll do show whole TNB frame. Okay, so you can see up here, it says TNB. So these are just approximations to 2 decimal places for those 3 vectors. Let's see, we don't need the 3 planes. Okay, well, the labels and equations. Continuous, no. Okay, so let's go ahead and look at this over here, and let's see what this looks like. Okay, and maybe I can even zoom in a little bit as it goes along. Okay, there, so you can see the tangent moving along. Notice how the normal is always pointing in the direction that the tangent is moving. Let's do it one more time. And then the binormal is always pointing in the, according to the right-hand rule, orthogonal to each of those. So it's this 3-dimensional coordinate system that moves along the curve. Let me add the osculating plane, and I think this will even give it a little bit more depth, because then you can see how the binormal is perpendicular to that osculating plane. Okay, so see, so that's the plane spanned by T and N, and you can see, so that's the plane that the curve, close to a point, that's the best plane that the curve lies in. And there we go. Okay, so that's what it looks like. And you can go back to, if we take a particular value of t, say at t equals 0, you can see here. So if you plug in 0 into the equations, what you'll see is that you should get 0, 1, 1 over square root 2 for the tangent, unit tangent, and so 1 over square root 2 is about 0.71. So that fits for the tangent. The normal, if you plug that in, you'll get minus 100, which it is there. And then you get this, the binormal is 0, minus 1, 1 normalized, so 1 over root 2. So that makes perfect sense there. Okay. So what we're going to do now is calculate the TNB frame for another famous curve. This is almost as famous as the helix, the twisted cubic, but only at 2 particular values of t, and you'll see why. We're only doing it for 2 values of t. And we'll take a look at that one too, and then I just want to go through just a few other curves, interesting curves, so you can see this coordinate frame as it moves along the curve. Alright, so again, we're going to start with the vector derivative, the velocity vector, which in this case is going to be 1, 2t, 3t squared. Okay, so far seems straightforward enough. Now when we look at the length of this, though, this is where it gets a little bit trickier because the length is not constant, obviously. It's going to depend on t. So it's going to be square root of 1 squared plus 2t all squared plus 3t squared all squared. So 1 plus 4t squared plus 9t to the 4th. That means the tangent, the unit tangent, is going to be 1 over that square root 1 plus 4t squared plus 9t to the 4th times 1, 2t, 3t squared. Okay, so far maybe it doesn't even look so bad now. We've got the unit tangent, we could plug in 0 and 1. But what about the unit normal? So the only formula we have so far for the unit normal is to differentiate this t and then divide by the length. As a function of t, so this is where it gets a little bit tricky because it's a scalar function times a vector function. So what we have to do is use the product rule. So we're going to find the derivative of t, but we have to use one of those versions of the product rule. If it's a scalar times a vector, it's first derivative of the second plus second derivative of the first. Now, the first here is just the 1 over that square root. So I'm going to write this as 1 plus 4t squared plus 9t to the fourth, all to the negative 1/2 power. Okay, so 1 plus 4t squared plus 9t to the fourth, all to the negative 1/2. So that's first derivative of the second, so that's 0, 2, 6t, plus second derivative of the first. Let's do the derivative of the first first. So we have to differentiate this thing to the minus 1/2. So it's going to be minus 1/2. All of this stuff to the minus 3/2 times the derivative of what's inside, which is 8t plus 36t to the third power, times the 1, 2t, 3t squared. Okay, now this just is a little tedious algebra. So the first thing we can do, so there's a 2, we can make that 4, 18. And then what we have to do is we're going to factor out this whole mess to the minus 3/2 power. So let's go ahead and do that. So I'm going to factor out 1 plus 4t squared plus 9t to the fourth, all to the minus 3/2. Now remember, when you factor that out, we're going to be left with just a 1 plus 4t squared plus 9t to the fourth, all to the first power here. So from this first term, we've got 1 plus 4t squared plus 9t to the fourth to the first, times the vector 0 to 6t. And then we've got a minus 4t plus 18t cubed times a 1, 2t, 3t squared. All right, so it looks like this might be worse, but it's actually not so bad, because now it's just a matter of distributing, and these are just polynomials. So from the first, we've got 0, because it's just 0 in the first component, and then we've got minus 4t minus 18t cubed. Okay. Minus 4t minus 18t cubed. Let's see what we got for the second one. We've got to multiply this whole thing by 2. So 2 plus 8t squared plus 18t to the fourth. And then from the second one, we've got 2t times all this stuff here. So minus 8t squared. And then it looks like we've got a minus 36t to the fourth. Okay, and then the last one, oh, it's going to be 6t, distribute the 6t across, 24t cubed, and a 54t to the fourth. And then from the second vector, a minus 12t cubed and a minus 54t, sorry, this should be t to the fifth, minus 54t to the fifth. This looks really bad, but a lot of stuff ends up canceling. So, for instance, we've got that goes away with that. Got the 54t to the fifth minus 54t to the fifth. Okay, the 24t cubed minus 24t cubed is just going to make plus. Or sorry, the 24t cubed minus 12t cubed makes plus 12t cubed. So I'll just put a plus there and get rid of that. And I think that's the, oh, and then we've got 18 minus 36, so that's going to make a minus 18, so I'll just change this to a minus, and that'll go with that. So I think this is all the canceling we can do, so let's see what we have now. So we've got still this 1 plus 4t squared plus 9t to the fourth to the minus 3/2 times minus 4t minus 18t cubed. Then we've got 2 minus 18t to the fourth. And then lastly, 6t plus 12t cubed. Now, this looks really bad, and to be honest, it is a little bit. But remember that we're only caring about 0 and 1. So what we're going to do is, instead of trying to normalize this, which would be awful, this is not the way you want to go, even if you want to do it in general for t. what we're going to do is just plug in 0 and then normalize that, and then plug in 1 and normalize that. So in fact, let's just say we're just at t equals 0. Let's just finish, we completely finished the whole TNV for t equals 0. So to do that, what we're going to do is notice that, so for t equals 0, we already have t of 0, because we can just plug in 0 up here. So we saw that that would be 1, okay, it's just going to be 1, 0, 0 all over 1 over square root 1. Okay, great. So 1, 0, 0. Now, what about the normal? Well, the normal is t prime of 0 over norm t prime of 0. And then we can just plug in 0. Okay, so 1 plus 0 plus 0. Okay, so that whole stuff to the minus 3/2 on the outside, that's just 1. And then what do we get inside here if we plug in 0? Just 0, 2, 0. So it's 0, 2, 0, divided by the length of that, which is just 2. I mean, you don't even have to kind of compute that. You can see it's length 2. In other words, we just get 0, 1, 0. So what we've seen here is, for the tangent and the normal, we're just getting I and j. And then we don't even need to do a calculation for this. We know that I cross j is k. So that means our binormal is going to be 0, 0, 1. So the TNB frame at t equals 0 just agrees with the regular IJK orthonormal basis. Now, what about t is equal to 1? So now there's a little bit of calculation to do. But we're going to go through the same steps. So t of 1. So I go back up here and plug in 1. Come on. Okay, so we got 1, 2, 3. And then it's all going to be divided by square root of 14. Yeah, 1 plus 4 plus 9. Okay, 1, 2, 3 over square root 14. So I'll just write that as 1 over root 14, 1, 2, 3. For the unit normal. Okay, so this is the tricky one. So I'm going to put in t prime of 1 over length t prime of 1. So what is t prime of 1? So I go up to what we got here. So right here. So I plug in 1. That's going to be 1. Okay, so that's going to be 14 again. So it's 14 to the minus 3/2. So it's 1 over 14 to the 3/2. But as we're going to see in a second, that doesn't really matter. So I'll explain in just a second. And then we get negative 22. 2 minus 18 times 1 is negative 16. And then 18. Now, it looks like I need to normalize this. And so normally I would. No pun intended. But remember that the whole purpose of normalization is just to get a unit vector in the same direction. And so if I'm going to normalize, I might as well normalize a nice vector that's a positive scalar multiple. I can change a scalar multiple, a positive scalar multiple, and it's going to normalize the same way. So I can completely actually just ignore, I can ignore this 1 over 14 to the 3/2 as far as normalization. And I can even multiply through by any positive scalar here. So I could factor out 2. So really I'm just going to normalize negative 11, negative 8, positive 9. And so if you find the length of that vector, let's see, so 121, 64, and 81. We just have to add up these squares. 16, 266. Let's see, 266 is, I don't think this is divisible by, yeah, so this is not divisible by any square. So when we normalize it, we're just going to get 1 over square root 266 times negative 11, negative 8, 9. Now I'm actually going to go ahead, actually for both of these, I'll go ahead and approximate these just to 2 decimal places. So this one is 0.27, 0.53, and 0.80. All right, so that's approximation there. And then this one, 1 over root 266. All right, and then times negative 11. That's going to be approximately minus 0.67, followed by minus 0.49. So one reason I'm doing this is when we get a calplot 3D, we can actually pause the video at t equals 1 and see that this is the calculations I get as well. And then positive 9 is 0.55. Okay. Now, for the binormal, we take the cross product. So it's the I, J, K. And the nice thing here is that, remember, since we've got the 1 over root 14, 1 over root 266, we can just take all of that out here. So 1 over root 14 times root 266. And I think that'll simplify a little bit. But in any case, we just take that out. So we're just crossing 1, 2, 3 with negative 11, 8, 9. So I'll go ahead, I'm going to pause the video and do this because it's not worth taking up time with the video. Let's see what we get. So we end up getting this, and you may notice, actually there's some nice canceling that happens here, because I got 14, so that'll make 1. 42 is 14 times 3. It's 3, 3. So I actually get something that's really not so bad. It's 1 over root 19 and the vector 3, negative 3, 1. And let's get some approximations for this as well. 3 over square root 19 is about 0.69. Okay, so 0.69 minus 0.69, and then 1 over root 19 should be about 0.23. Yes, it is at 0.23. Okay, so we've got exact expressions here, and now we've also got some approximations. Let me go ahead and box these off for safekeeping, and then we'll go ahead and look at the graph of this. Okay, so those are 3 of them. My writing really has a tendency to go up, because I need to watch that. Okay, so let's take a look at this curve. Okay, so before I start it, let's just check out our 3 vectors for t equals 0 and 1. So here I'm at t equals 0, and you can see there it says t and b is I, J, K. Not sure why they put a plus on the plus 1j, but they did. So that agrees with what we got. Let's go to t equals 1. Okay, so that's out here. Maybe it's not going to stop exactly at it. Maybe I can type in 1. Okay, so there we go. Okay, and we get 0.27, 0.53, 0.8. Okay, so this agrees exactly with the approximations that we got. So if you see those 3 numbers up there, you can see that agrees exactly with what we got. So, looking good so far. Let's go back to down here. Actually, we'll just do this minus 1.5 to 1.5. So let's see what this looks like. There it moves along. Now notice it's going to kind of twist. That's why it's called a twisted cubic. It's going to twist along there. And there it goes. And it's going to go off forever. Maybe look at it one more time. Slightly different perspective. kind of looking from below. Goes, and off it goes. Goes that way. Okay, so that's what that one looks like. So to wrap up here, let's just for fun, let's just look at a few other ones. Let's see. So this is one we looked at earlier. This was in the space curves section. Now this one, let's see, I really only goes from -1 to 1. Let's go back here. So let's take a look at what this one looks like as we go through, and you can see the frame and the oscillating plane going through. Maybe speed it up a little bit. That's a little slow. A little bit slow. Okay. Start over. There we go. You can see it as it goes around there. Got it one more time. Okay, and let's look at one more. So this one is kind of the default curve that's given when you turn on the space curve on CalcPlot 3D. You can see it over here on the left. So let's go ahead and start this one off. Oops. Okay, and you can see it moving along there. Slow it down just a hair here. Too fast. There's a good view. You can see it moving along. So I'd really encourage you, I've given you this website, and I've kind of shown you how to do this. Just play around, find some other curves, or just enter in some interesting functions in here, and just see what these look like. Make this continuous. Just see what these look like for these TNV frames. I just think it's kind of interesting to visualize these. So hopefully this gives you a good sense of what this is, even though we haven't really gone into too many calculations. There's better ways to calculate these, but that would really be for another class. So hopefully you have an idea of this if you see this idea again in the future.